Hi, my name is Manish Gupta, and in this video, I'm going to talk about Parabel, which is an algorithm based on partitioned label trees for extreme classification. So let's get started. Okay. So we will talk about how does Parabel broadly work. Let's begin with that. Okay. So in the previous video, I talked about DISMAC, and there have been other such one versus all classifier based approaches for extreme classification like PPD sparse, sleek, and so on. Okay. These approaches sort of train a separate linear classifier per label, and they have high prediction accuracies. However, their training and prediction costs are linear in terms of number of labels. Although DISMAC basically proposed distributed training, still the training algorithmically is linear in terms of number of labels. Okay. Tree-based approaches have their own benefits. They essentially learn trees leading to logarithmic prediction time, right? However, tree-based approaches have not been as accurate as in one versus all approaches, and that is why folks proposed Parabel in 2018. Okay, so Parabel learns a balanced label tree. Unlike previous tree-based approaches, Parabel does not create trees in the feature space, in the data point feature space, but it creates trees in the features in the label space. Okay. And it also promises the log time training and prediction, just like other tree-based approaches. Of course, they are much better than these one versus all approaches in terms of accuracy as well, as we'll talk towards the end of this video. Okay. So how does Parabel broadly work? Well, there is a training phase and there is something to talk about inference. So let's start talking about the training. Right. As I mentioned, Parabel is a tree-based approach. In fact, it learns a small ensemble of up to 3 label trees only. So unlike other approaches like FastXML, which essentially learned a larger number of trees, Parabel just learns an ensemble of up to 3 label trees. Partitioning is done in the label space, and partitioning is done into two balanced groups. Now, of course, you can actually have it M-way tree as well, but in this video, I'll just talk about two trees. So, so partitioning is done in the label space. So you partition some labels on the left child, and some of the labels go to the right child. You continue to grow the tree, doing this partitioning, at different nodes until the leaf nodes essentially have just up to m labels. If the node has more than m labels, you split further. Otherwise, you just stop. Okay. Now, leaf nodes contain linear one versus all classifiers. You basically have one versus all classifiers, but they are only in the linear in the leaf nodes, right? Essentially, they don't really, they are not as large in they don't work in the entire label space. Remember, a leaf node basically just manages up to m labels, and therefore these one versus all classifiers run super fast. Okay. Now, of course, they contain linear one versus all classifiers, one per label. So one for each label in the leaf, of course, which are trained on only those examples having at least one leaf node label. Okay. So essentially, Parabel is a tree-based approach. It creates a balanced label tree. So partitioning is done in the label space. Um, Now, how is the inference done? So at the inference time, you essentially take a data instance. You traverse the label tree. Of course, you start from the root node. Each internal node, just like there are one versus all classifiers at the leaf nodes, there are also one versus all classifiers at internal nodes themselves. So each internal node learns two linear classifiers indicating whether the test point, the new data point that has come in, should actually be passed to the left child or to the right child or both of them. Now, a test point, can actually traverse both of those paths, and therefore, a test point can traverse multiple paths to the entire label tree to reach to multiple leaves. One versus all classifiers in these leaves will determine the probability that the test point is going to belong to a particular label, which is relevant to the test point in that leaf node. Okay. And you have up to 3 label trees. So you're going to average out these prediction probabilities across several trees in the ensemble, and that's going to be your overall probability distribution from which you can actually predict top few labels as labels which are relevant to this new test point. Okay. Now, there are some details in the algorithm to be talked about. So how is this label tree learned in Parabel? Okay. So to be able to learn a label tree, the first step is to actually learn a good label representation. So you essentially take a label. The label essentially, a label is represented by a unit vector in the direction of the mean of the training points containing the label. So let's say if the task is a Wikipedia categorization task, so you have a Wikipedia page as an input data instance, and you want to figure out which of the categories can be used as the label. So for a particular label, let's say cities in India, you would basically take all the pages which have been labeled with this category. It could be Mumbai, Hyderabad, Calcutta, Delhi, and so on. And then you take the label representations, take the representations for those training points, and you average them out, and then you normalize by the magnitude of this vector so as to essentially get a label vector for the label cities in India. Okay. Now, for each of the training points in Parabel, they propose to use the TF-IDF vectors, but you could literally use any other embedding that you may want to that you may want to use for each of those training points, and then average them out so as to get the label embedding, um, and then divide by the magnitude so as to essentially get a unit vector, which represents the label. Okay, so this is how you get label vectors for each of the label in your data set. Now, that's the label representation. Now, how do you do label partitioning? So remember, if you are at a particular node, starting from the root node, you want to partition it into the left and the right child. Again, in this video, I'm talking about k equal to 2. I mean, two children, but then this algorithm is generally applicable to multiple children as well. Okay. So label partitioning in Parabel happens using spherical k-means. Specifically here, k is set to 2 because you want two clusters of labels, such that these labels are as close to each other as possible. Now, again, the reason you want to do this clustering is to ensure that those labels and those data points which are very related to each other, they belong to one cluster, and therefore they go down one path of the one subtree in the tree, and those which are different go to the other subtree in the tree, right? So there is this spherical k-means happening here, as you see. So what do you do? What you want to do is to maximize similarity of each of the data point with respect to its cluster centroid. So essentially, since you have two k equal to 2, therefore you have two cluster centroids, mu plus and mu minus. And what you want to do is to take those label vectors, and essentially you want to ensure, that if a label vector is positive, it must be closer to the positive centroid. If a label vector is negative, it must be closer to the negative centroid. So here alphas essentially are also going to be the output of the clustering algorithm, and alphas essentially denote whether the point belongs to the positive cluster or the negative cluster, or in some ways, whether the point should go to the left child or the point or the label should go to the right child. Okay. So mu's are essentially centroids, and alphas are the cluster assignments. And what you want to do is to maximize the similarity between any label and its cluster centroid. Okay. You also want to ensure that the tree remains balanced, and therefore these alphas, the sum of these alphas should be between -1 and 1, so as to ensure that maybe one of the left or the right child is just one more or less compared to the other child. Okay. Now that's that. So that is how label partitioning is done. You start from the root node, you partition it into left and right child, and you follow the same trick for the entire tree construction. Okay. Um, Now, if you think about any particular data point, whether it is a training data point or a test data point, it is associated with multiple labels in the extreme classification setting. Extreme classification, recall that extreme classification is a setting where each data point belongs to multiple labels, which are a subset of the entire large label space. And since the label space is large, it's called extreme classification, right? So now, so whether it is a training point or a test point, it is related with multiple labels. And if you look at this tree, now these multiple labels could belong to multiple leaf nodes. Okay. So if I start from the root node and I want to reach to these leaf nodes, which contain relevant labels for this particular data point, I will need to traverse multiple paths. Let Zn equal to 1 indicate if a node n was traversed while doing this kind of traversal on the tree. Okay. So Zn equal to 1 indicates whether the node was traversed or not, right? At train time, you actually know which nodes are traversed. At test time, of course, you have to figure out what those nodes are. Okay. So let Zy be the set of paths which can lead to Y being sampled. So Y is basically the set of labels which could be associated with a particular data point X, right? So if you have a data point X and if you have the label set Y, let Zy be the set of all those paths which are being, which can lead to Y being sampled. Okay. Then you can basically indicate the probability of Y given X. Now, what we are trying to do is to figure out how to learn these one versus all classifiers in the various nodes, the internal nodes as well as the leaf nodes in Parabel tree. Okay. So the way it is done is by maximizing the data likelihood, and that is why we are trying to figure out this data likelihood guy, a probability of y given x. So probability of the labels given the data points can be expressed in terms of these z's on the way. Okay. So so this is basically just the typical chain rule of probability. So sum over all z. So whichever be the paths, you essentially want to take various paths, and um, you want to reach those leaf nodes which contain labels in y. So sum over all z, probability of y given z comma x, and probability of z given x, right? So essentially Zn equal to 1 is a random variable. Zn can take only two values, Zn equal to 0 or 1. It's 1 when node n was traversed and 0 when node n was not traversed. Okay. Now, what I could do is to basically split this and write it in this way. So essentially, I don't care about all z. So because if z is 0, if it was not traversed, then I can safely say that hey, if a particular node was not traversed, there is no way that I will be able to essentially have any probability of um, assigning or sampling a class label which does not relate to the paths that were traversed, right? So therefore, I will basically just care about those z's which belong to zy, right? So only those nodes, internal nodes also have a z value, leaf nodes also have a z value. So I care only about those particular nodes which lie on the paths which lead to labels related to the data point x. Okay. So now, while traversing these paths, there are a few things, right? The first thing is that you have to traverse the entire path, internal nodes. So I will call the set of internal nodes as I, and the set of leaf nodes as L. Okay, so while traversing those paths, what do you want to ensure? You want to ensure that the path has been traversed. So in the sense that you have to first care about generating, probability of so first the path must be traversed, and second, once you reach a leaf node, the right labels should be sampled. Okay, so let me first talk about these leaf nodes. That's easier to talk about. So the idea is that the leaf node should be traversed, and therefore Zn should be 1 for that leaf node. And I'm multiplying over all those leaf nodes. So I care about the probability of each of those leaf nodes, right? So all of those leaf nodes. Okay. Um, where Zn is equal to 1. So the Zn has to be 1. And then what is the probability of sampling a particular label yn, right, given this particular leaf node? So I've reached a leaf node n, and n, right? N is the leaf node. And Zn equal to 1. That basically means that I've reached that leaf node. From that, I have to basically sample a particular label. Remember, a leaf node could actually have up to m labels, and not all of them may be relevant. So I have to sample a particular label or a few labels, right? So therefore, I multiply over all of those labels which can be sampled and their probabilities. And that's basically a part of this of this factor, probability of y given z comma x. Now, probability of z comma x essentially is about dealing with the internal nodes. So when I'm dealing with the internal nodes, I want to ensure that I am actually traversing the root node, going to the right internal nodes, which finally will lead to y's being sampled, to the leaves, to the right leaves being reached, right? So as I basically traverse to these internal leaf nodes, I have to ensure what is the probability of the right children firing up, given that the root node has already fired up. Okay. Or the parent node has already fired up. So given that the parent node is traversed, what is the probability of traversing particular children, right? So particular children. So that's basically that second factor. Okay. So that is what overall will determine my data likelihood. Okay. Now, this data likelihood is what we are going to use so as to define the way to really create these label classifiers, both for the internal nodes as well as or other one versus all classifiers, both for the internal nodes as well as for the leaf nodes. Okay. Now, specifically in this video, as I mentioned, I'll talk about this case where k equal to 2. That is, I'll only have a left child and a right child. But also, if you set m equal to 2, m equal to 2 meaning, your leaf nodes basically contain only one label, remember, okay? So m equal to 2 basically means you have a binary label tree such that each internal node has only two children because k equal to 2, and each leaf node has a single label because m is equal to 2. So now, if the internal and the leaf node distributions, right, are set to logistic sigmoid, if you basically learn those classifiers such that they follow logistic sigmoid laws, then multi-class, then this particular Parabel tree or this learning is exactly the same as multi-class hierarchical softmax. Okay. So that's the equivalence between the way Parabel label tree works and the multi-class hierarchical softmax. Anyway, now coming back to how are these classifiers per node learned in the Parabel tree, right? So I already motivated how the data likelihood can be computed. Now, learning the classifiers per label node in the Parabel tree is about learning the parameters of the internal and leaf node distributions, right? So essentially, remember, you have these two factors, probability of y given z comma x and probability of z given x. These are leaf node as well as internal node distributions. And what you want to do is to basically put up a form for these distributions and then learn those parameters. Okay, they are all independent one versus all classifiers. Um, and they must be learned, by using some optimizations, right? So that is what I'll talk about on this slide. So on this slide, on the left side, what you see is, how these things are done for the leaf node. And on the right side, what you see is how these things are done for the internal node, how these classifiers are trained for the internal nodes. Okay. So let's talk about leaf nodes now. So for the leaf nodes, long story short, well, this is the thing that you're going to minimize so as to train the classifier W. We are going to represent the classifier using a vector W, vector of weights W. So you're going to train this logistic regression classifier W um, using by minimizing this factor, this particular optimization, this particular objective function. Okay. So in this minimization, you see two terms. So the first term essentially is just for L2 regularization, so as to ensure that your Ws don't grow too large in that senses, right? And the second term essentially tries to minimize the logistic loss. So here, essentially, a little bit of a notation here. So xi stands for the data point clearly, right? W essentially stands for the weights in this label in this classifier. Okay, so and then you have ing. Now, what is ing, right? So ing can only take two values, 0 or 1. So it basically is 1 if label L in a node n, in a leaf node n, is relevant to xi. Okay, so in a particular leaf node, you have reached that leaf node n, and there is a data point xi. And if a particular label L out of m possible labels, remember, so there could be m possible labels in the leaf node. Out of that, if a particular label L is relevant, YINL is going to be 1, else it's going to be 0. So there are many other labels in that leaf node, specifically m-1 labels in the leaf node, and only one of them is relevant, the others are not relevant. Okay, so what does this loss do really, right? So you're trying to, of course, minimize it, so it must be a loss function. So what is this loss doing? Well, so if y is equal to 1, okay, what is y equal to 1 mean? Y equal to 1 means that this particular label is really relevant. Then what would happen? So if y is equal to 1, then you would want to ensure that the similarity between this w and this x is very high. So you want, it's just the same one versus all classifier. So you want the similarity to be high between the weight vector and xi if y equal to 1, right? If y is basically equal to 0, meaning, this particular label is not relevant for the for the classifier, for the label L, right? So this particular label class not relevant to the data point. In that case, what would happen is, y equal to 0. So basically this entire factor, 2 into 0 minus 1 becomes minus 1. And you would end up minimizing the similarity in the sense that you would want that W should be as far away from the data point as possible. Okay, so in some ways, what are you trying to do here? You're trying to learn a label classifier by asking the optimization so as to ensure that those weights should be as close to data points, relevant data points as possible, and as far away from non-relevant data points. Again, these non-relevant data points are hard negatives. Remember, why are they hard negatives? Because these non-relevant data points actually lead you to the same leaf nodes. But but the other labels in these leaf nodes are sort of not really but you want to ensure that these data points which are relevant to this label L are not relevant to other labels in the same leaf node. Okay, so therefore, the way you're defining this loss, you're ensuring that you learn a classifier which is similar to data points related to this label and far away from data points related to labels in the same leaf node, but other labels. Okay, so that's about the leaf node classifier, the leaf node one versus all classifier. Okay, how do you train this classifier for internal nodes? Now, for internal nodes also, the form remains the same. So essentially, you're still going to use the same logistic regression kind of classifiers. You're still going to do the L2 regularization. However, the only thing that change is how do you define, how do you define what you want to optimize for. So how do you define some sort of a label for these logistic regression classifiers? Now here, this ZICNJ is equal to 1 if child j of node n was traversed, and otherwise you set it to 0. Okay. Essentially, for node n, there are several children. When k equal to 2, there are only 2 children, but otherwise there are several children. And ZICNJ will be set to 1 only if child j of node n was traversed, else it is set to 0. Okay. In some ways, what this classifier is going to do is essentially it is going to train an independent, an independent linear classifier is trained at every child to separate the training points, reaching that child, and it tries to separate it from training points which are its siblings. Okay, so the left child versus the right child, whatever training points are there, it sort of tries to learn a nice separator, nice logistic regression separator between the two. Okay, so that's how Parabel does. That is how basically the parameters of Parabel are learned. Okay. Uh, so we've talked about how the Parabel tree is constructed. We also talked about how the leaf node and the internal node classifiers in Parabel are trained. Okay. Now, how are final labels predicted by Parabel at inference time? So what happens at inference time, right? So at inference time, what you want to do is to figure out what is the probability of any particular label equal to one given x. So you have a test data point coming in. You want to figure out amongst, let's say, 100K labels, which of those labels are relevant. So what is the probability of YL equal to one given x? Now, of course, this can be written down in this form. So essentially, what you want to do is to first reach the leaf node, which contains the particular label. So probability of y equal to 1 given z equal to 1 given x, comma x, right? So you must reach the leaf node. So, and if you reach the leaf node, what is the probability of sampling this label given the leaf node? And then how do you reach the leaf node? Well, you reach the leaf node by traversing the appropriate path starting right from the root node. Okay. So what is the probability of starting from the root node, really going to that particular branch from the root, which leads to finally leads to the particular leaf node n, which contains the label YL. Okay. Label L, right? So essentially, so this particular part is recursively traversing from the root node right to the appropriate leaf node. Okay. On the way, of course, you want to make use of these logistic regression classifiers so as to decide whether to go left or whether to go right and so on. Now, if you do this for all of those your labels in the label set, I mean, your labels are too many because it's an extreme classification problem, so that's not going to work out, right? So therefore, you have to have some faster way of checking these probabilities only for a few number of labels. Okay. So the way you do that is using beam search. You essentially start from the root node. The assumption here is that you, or rather the way you do this is to predict only the top ranked relevant labels. You're not going to come up with probabilities associated with all the labels in the entire label set. You're basically only interested in the top few labels. Most of the applications are like that. You basically want to predict only relevant documents, few relevant documents for a query, or few relevant keywords for a particular advertisement, or few relevant categories for a Wikipedia page, and so on. Okay. So you're only interested in the top few relevant labels. And the way you are going to do this is to greedily traverse the tree, starting from the root node and always keeping a track of the best P most probable paths, right? So most probable or the best P paths at each level in the Parabel's label tree. Okay, so start at the root node, you visit each internal node in a particular level, compute the probability of the path from the root to each of those children. And you store those probabilities, of course. And at any point of time, you are going to keep the P best paths. Of course, you stop the traversal when you reach P leaf nodes. So as soon as you reach P leaf node, those are your P leaf nodes, which are going to be the most relevant ones, and therefore you stop the traversal right there. Now, once you've reached the leaf node, of course, you are going to use this formula so as to essentially compute the marginal probability of a particular label at that leaf node, and then you're going to average out such marginal probabilities across all the T trees in your ensemble, and then which basically gives you the final list of the top ranked relevant labels from Parabel. So now that we have understood Parabel, how does Parabel perform? So Parabel performs 600 to 900 times faster in training and 60 to 13,000 times faster at prediction compared to DISMEC that we talked about in the previous video. Okay, so it's super fast. Let's call it that way. Okay, while maintaining the classification accuracy, while maintaining very similar classification accuracy, right? So classification accuracy wise, it's not improved, but then what improves significantly is the train time as well as the prediction time. Okay. So overall, if I compare it with the faster XML, PFAST re-ranked XML, right? Propensity scored fast re-ranked XML that I talked about in the previous video. Well, it takes up to 20x lower training time, 38x lower model size, and 9% higher prediction accuracy. So, I mean, in 2018, when this algorithm was proposed, it was the best algorithm in extreme classification. Of course, it was also the best algorithm from a label tree perspective, from a tree-based algorithm perspective for extreme classification. Now, they also experimented with dynamic search advertising, where the idea is that the problem is to find search engine queries that might lead to clicks to particular ad landing pages. So the input is an ad landing page, and you have to predict from the large set of 7 million sized set of queries, predict which of them are relevant. So your label space is pretty large here, 7 million, and you want to predict those queries which apply to this ad landing page. Now, they compare it with a simple BM25 based comparison. So of course, you can compute BM25 between the query and the ad landing page keywords, and that gives you some retrieval accuracy. Compared to that, you could also essentially compute features of the ad landing pages and give it to Parabel and try to ask Parabel just to predict the right label set. They compare on 4 different metrics, click-through rate. So click-through rate is what is the percent of times users actually click on the ads when a query was put up. Bounce rate, so percent of times a user clicked but then returned immediately to Bing after clicking on an ad. So, lower bounce rates is preferred, of course. Ad recall, so percentage of ads that were clicked by at least one user, and quality of ad recommendation, which is in some ways a goodness of the ad recommendation according to a query ad relevance model trained on human label data inside and proprietary to Bing. So what they observed is that compared to BM25, you get like 420% better ad recall and 120% higher CTR. Bounce rate is 68% relative to BM25, which is good because it should be lower, and relative quality of ad recommendation is almost similar to BM25. Okay. Okay, so in summary, in this video, I talked about Parabel. Parabel learns a balanced label tree, a balanced hierarchy over labels, which is both more accurate as well as more efficient, more accurate compared to other tree-based extreme classification approaches, but almost as accurate as DISMEC, which is a one versus all classifier-based approach. It comprises of a probabilistic model of the joint label distribution conditioned on the data point and the learned label hierarchy. We understood that essentially one versus all classifiers are trained for every internal node and every leaf node. It provides log time training and prediction by the nature of it being a label tree based approach, right? And we also observed that it improves the quality of dynamic search advertising on Bing by huge amounts compared to a simple BM25 based baseline. Okay, so that's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage.